Good morning, everybody. Welcome back to Roswell. Y'all, we're going to move on today and talk about some more identities. Now, I know it's easy for me to say don't memorize all of this stuff, folks. These formulas look pretty daunting. There's like 6 formulas on this page. Now, it turns out you can obtain all 6 of these from just a single one of them. Now, these have a wide range of applications in this course and also when you move forward and take calculus next semester. One of the big topics in calculus is you're finding derivatives, and a derivative of a function is just another function that tells you how quickly the original function changes. And so when trigonometry is a big deal in calculus, and we'll use these formulas to help us find derivatives of, say, the sine function, the cosine function, the tangent function. And again, for those of you who are familiar at all with calculus, this idea of a derivative is really, really big. And so you need these formulas to help you determine derivatives of the various trigonometric functions. Now, what we're going to do is start out assuming this one right here is given. Okay, in other words, I'm going to be switching back and forth between screens, but let me see if I can do some damage here. Okay, we're going to assume that this formula right here is given. Now, let me see if I can do better than that. Y'all, I'm just going to mark this one right here. We're going to assume that formula right there, folks, we're going to assume that it's given. Okay, let me see if I can. This is not like the good old whiteboards, ladies and gentlemen. Okay, given. Okay, again, now this particular result is something you could prove on the unit circle. And if I was seeing you guys face to face, I think I would spend the time to do it. It takes about 10 minutes to actually prove this. And you can draw these angles on the unit circle and actually prove this formula. But again, you've heard me say it before, in the name of time and in relatively short videos, we're just going to go ahead and assume that this formula right here, the cosine of alpha plus beta is equal to the cosine of alpha, cosine beta minus sine alpha, sine beta. We're going to assume that's given. And it turns out all these others, excuse me, all these other results that you see here can be derived. Now, we're not going to derive each one of them, but I'm just going to go through and show you how this one, you can start with this one and prove all the others. We're not going to do them all. And you could actually start with any one of them and prove all the others. It's kind of interesting in that sense. Okay, so let me switch screens, folks, on you. All right, there we go. All right, now, okay, ladies and gentlemen, again, what I did right here is I made the assumption that this formula right here was given. I don't like doing that because I'd really like you to see why this is true. But that top formula, we're going to go ahead and make the assumption that it's given. Okay. Now, so what we can do, you go, okay, well, we have a formula for the cosine of A plus B. How would you go about finding a formula for the sine of A plus B if this were known to be true? Okay. Now, let me take you down to this picture of this triangle right here. This goes all the way back to when we were still face to face. We have a right triangle right here. Okay, now you'll remember pi over 2 is just 90 degrees, right? Pi over 2 is just 90 degrees. And we know that the sum of the angles, the sum of the interior angles in a triangle sum up to 180 degrees or pi radians. So you can see 90 degrees plus 90 degrees minus theta plus theta all add up to 180 degrees. Now, the reason why this is important, you can see pretty quickly, remember the definition of cosine? The definition of cosine is the adjacent side divided by the hypotenuse, all right? We see, so the cosine of pi over 2 minus theta is equal to the adjacent side over the hypotenuse. But that's also the same as up here for sine. The sine of an angle is the adjacent side divided by the hypotenuse. So you see, in that way, we actually get that the cosine of pi over 2, I'm just rewriting it, minus theta is equal to sine theta. Okay. And again, y'all, when we graph these trig functions, we could see that they were out of phase. Like, for example, if theta were 0, the cosine of pi over 2 is 0, but the sine of 0 is 0. Or if theta is pi over 2, you get the cosine of 0 is 1 and the sine of pi over 2 is 1. So you know this is true just by substituting well-known quadrantal angles into the expression. But anyway, this is also what you could call this a mini identity if you want to. I mean, this is an identity. It's easy to establish. It's not as hard as some of the other identities, but it's an identity nonetheless. It reads the cosine of pi over 2 minus theta is equal to sine theta. Now, believe it or not, this comes in handy when we're trying to use this to prove this. And y'all can see what I did right here. And again, you can just follow it along. This pi over 2 minus a plus b is just using this formula right here, right? Theta is going to be your a plus b. All right. Now, a little bit of manipulation here, folks. You can rewrite it like this. Now, notice that I wrote this in a way that allows us to exploit the truth of this. See how I got a plus, a minus b? So you have this right here is in this form. It's just that a is your pi over 2 minus a. And then there's your b right there. And there's this plus sign. You see how it all lines up? And so what I'm doing from here to here is I'm just coming back up and using this right-hand side. Can you all see right here, the cosine of pi over 2 minus a goes right there. The cosine of minus b goes right there. You see this minus sign, so on and so forth. Now, here's where we use this truth right here. The cosine of pi over 2 minus a is just sine of a. Y'all remember cosine is what they call an even function. That was proven in class. Any even function just eats up the minus sign. Right over here in a similar fashion, the sine of pi over 2 minus a is cosine a. And also, remember the sine is what they call an odd function. So this minus actually came out and canceled this minus sign. And we have an identity now for the sine of a plus b. So this is the addition formula for cosine, and this is the addition formula for sine. Now, without writing all this down, you can see that if you just replace this with a minus sign right here, if you replace this with a minus sign, this would be the sine of minus b, and that would make that a plus. Okay, and the very same thing right here. If you replaced b with a minus sign, the sine of negative b would bring the minus sign out here. Okay, and you can go back. I wish I could go back and forth easier, but those are the 4 formulas that were on the previous screen. Okay, we've already proved it. Now, I could have written a lot more down, but basically, once you start from here and you couple this with this truth right here and properties about even and odd functions, you get all 4 of those addition and subtraction problems. Okay, and y'all, I'm just going to switch screens briefly. And I wish I could keep this together, folks, but it's not quite doing it the way I expected it to do it. So we're going to have to switch back and forth between screens. But anyway, I'll go back and again, folks, you see, this is what we just started with. They're using different letters. I don't feel like writing alpha and beta down, so I wrote the regular English letters down. But this is what we started with. And what I just showed you, we proved this, okay? From right here, we actually proved this statement right above it. And you see how the signs just changed? They all are about the same here. Like you got a minus here, but the only thing that's different is this minus sign right here. Right here, you got a minus that changes to a plus, okay? So again, they're not quite as hard to remember as you might think. And I will expect you to have these memorized. I know it sounds like a lot, but once you know one, you kind of know them all. Now, I may have time to prove these for you. These proofs aren't particularly difficult once you know all this stuff above is true, okay? But so anyway, let me switch on back to the next to our work screen. Okay, here we are. Now, let's see here. Okay, are we doing good? All right, now Your screen sharing is paused. All right. Okay, y'all. Here we go. Now, so what I want to do right now is talk about some applications of this stuff, y'all. I'm going to make this a 2-day procedure because this is pretty bulky and there's quite a few so-called applications of all of this. But one thing we might be curious about is, you remember all we did was we learned all the nice angles. Remember 30 degrees or pi over 6, right? 45 degrees or pi over 4, and 60 degrees or pi over 3. Okay. Now these are the so-called nice angles, and you recall how we learned all the trig functions of all of these, like the sine of pi over 6 is 1/2, for example. Cosine of pi over 4 is square root of 2 over 2. The sine of 60 degrees is the square root of 3 over 2. Okay, we proved all that in class way back when. That's been almost 2 months ago. Now, what we can do with these new formulas is actually come up with the exact values for angles other than these nice angles. And let me give you a concrete example. Now, an identity and I'll just write it down so we can see what we're doing here. Okay, now, y'all notice here we have a minus sign, up here we have a plus sign, but based on what I was telling you earlier, all that really happens here, the only real difference, okay, not too hard. Now, again, folks, if you were just thinking about given this one is true, if you put a minus b right there, cosine of minus b stays the same, okay? But if you put a minus b right here, and I've said this once already, the minus sign comes out to the front and makes this a plus sign, okay? See, y'all, it's a subtle difference between this one and this one. And you can see it from here. If you take this to be true and you put a minus b right here, the sign of minus b hangs onto the minus sign and changes this sign to the plus that you see right there, right? Now, let's take a look at how something like this might be useful in terms of expanding our list of so-called nice angles. Okay, we could write down the cosine of 15 degrees. Okay. Now, that's equal to, and y'all, I'm going to drop the degrees right here. That's equal to the cosine of 45 minus 30. Okay, see there, ladies and gentlemen? Okay, that's equal to the cosine of 45 minus 30. Now, so what? 15 degrees is equal to a lot of things. It's also equal to 60 minus 45. It's equal to 105 minus 90. Why are these so important? Well, we happen to know the trig functions of these nice angles, right? 45, 30 are among our so-called nice angles. And so what we can do right here is just hand this off directly to the problem right above. We can write down the cosine, or the identity right above, cosine of 45. Again, y'all, I'm dropping the degree notation just to avoid the clutter here. Cosine 30. Okay. Plus the sine of 45 degrees. Sine of 30 degrees. Okay. So, y'all, we use this so-called subtraction formula, you know, even though it involves addition right here, to actually come up with a clean way to find out what the cosine of 15 degrees is. Okay. Now, y'all, this is kind of a big deal, at least theoretically. Y'all can just punch it into your calculators. But the presence of these formulas gives you a way to keep taking halves of all of these values. Now, okay, let's take a look at what's going on here. Cosine of 45 degrees is root 2 over 2, if you guys remember from your unit circle developments. Cosine of 30 is what, root 3 over 2? Remember, y'all, as the angle gets smaller, the x coordinate gets bigger, right? That's how I remember it. Sine of 45 degrees is root 2 over 2. Sine of 30 degrees is 1/2. Okay. Now, as far as the math goes, I mean, right here you could, and y'all, I encourage you to actually check this on your calculators. In fact, I'll write that down as a homework problem. Just check this on your calculators, verify on calculator. Let me write this off the side. Homework number 1. Verifying. Y'all, this is a quick, I don't know. I mean, I guess just to make sure you're doing it, I'd like to see a screenshot of your calculator or something. Just take a pic or something and drop it in. Okay, I just want to make sure you're seeing that this all lines up. Now, but I'm not saying any of this just yet. I'll tell you what I mean in just a minute. But now, y'all, what I notice right here, now everybody does their algebra slightly differently or their arithmetic, but notice that root 2 over 4 is common to all of these terms. You see, you have a root 2 here, and you have a 2 times 2 here, you have a root 2 here, and you have a 2 times 2 here, right? So root 2 over 4 is your least, or your, what do they call that? The greatest common factor. So what you have right here is root 3 left over plus 1. You know, that algebra or arithmetic, whatever you want to call it, seems a little tricky. But really, if you just take a look here, root 2 is common to both terms, right? 2 times 2 in the denominator is common to both terms. So this is how you would simplify this algebraically. Now, what I want you guys to do, as far as this homework problem goes, is just find out what this is as a decimal. Okay, find out what this is as a decimal. Take it out a few places just to be, you can take it out to 3 places if you want to the nearest thousandth. Not super important there. Okay, but then on your calculators, make sure you're in the degree mode. Just, okay, do this and then also compare that to what you actually get cosine of 15 degrees. Okay. And again, y'all, it's a fairly simple exercise, and you can, I know it's kind of a pain for you, but I wouldn't mind seeing that if you could, however you can get that displayed, or just confirm that you did it, but I need to know you're staying active on this stuff. So again, you can just directly put this in your calculator, get a decimal value, and then compare it to this exact value. All right, and again, maybe go to 3 places, just to 3 decimal position, level of accuracy, 3 places, you will. Okay. And again, that's your homework problem number 1. Okay. Now, let's take a look. And again, y'all, I'm going to try to split this up into 2 lessons. But what I want you also to do for your homework is I want you in a very similar fashion to homework problem number 2. Determine what the sine of 15 degrees is. Sine of 15 degrees. Now, for that one, for the sine of 15 degrees, what you'll be doing would be this formula right here, and I'll just write it down here for you just for the sake of clarity. You'll be using the sister identity, if you will, sine of a minus b. You know, I'm always working to make sure I don't run out of room here. This is kind of cramped quarters. Now, y'all, we go to this formula right here. The sine of, this says the sine of a plus b, right? Sorry. This one here says the sine of a plus b equals to this. Now, as you may have anticipated, all that's going to change right here, if you put a minus here, it's going to change that to a minus. It's kind of the opposite of the other one. It is the opposite fact. So what I'm going to do right here is write down the sine of a minus b equals to, it's very, very similar to what we just did. minus the cosine of A. Am I still on the screen, folks? Here we go. Good enough, folks. Now, again, all I did, folks, is just this literally came from what we just proved, 10 minutes ago. It came directly from this. If you put a minus right here, that's going to change this to a minus, which doesn't change the cosine function. But the minus right here will, since sine is what they call an odd function, will bring the minus out to the front, okay? So that's exactly what happened right here. So you see, as nasty as all this looks, it's actually fairly connected. So homework problem number 2, I want you to do this. And again, go ahead and compare your exact value with whatever your calculator returns. Okay, just to make sure you trust this stuff. Now, folks, just as an aside, as a thought thing, and I'm not going to assign this, but I want you to be thinking about this. You see what the implications of this are? Now that we know, after this, you would know what the sine of 15 degrees is. Or let's come back up here. We know what the cosine of 15 degrees is. It's equal to this. Okay. Now, do you see how this 15 is half of 30? All right. Just like we use 30 to get this, we can use this result to get the cosine of half of this, right? Now, I'm not going to assign this, but if you do have time, you may want to experiment with that too. Or do you see, now we have the methodology to take halves all the way down. Once we know this, we could find the cosine of 3.75, right? And so on. So again, the expressions get kind of nasty to work with algebraically. But once you take half of something, that means you got a process, right? So you can keep halving and just use the original, the previous input for the new input, basically. Okay. So again, not an assignment, but just this leads to what they call half angle formulas. Okay, half angle formulas, which I'm trying to cram in all into this lesson. Okay. So again, we got 2 homework problems now. Homework problem number 1, homework problem number 2. Okay. Now what I want to do, and again, this will be the last part of this lesson because it is quite a bit of stuff. Let's take a look at how we might produce some other formulas. They're called double angle formulas. And let me switch over. Let me turn this sheet over. Okay. Or double angle identities, actually. Yeah, let me see if I can. Now, all right. Yeah, let's start out with the sine of A plus B. And y'all, what I'm going to do right here is I'm going to assume that A equals B. I'm going to use a new letter, X. Okay. Now, in other words, we're talking about 2 angles that are the same thing. So that our formula, the sine formula, would become the sine of X plus X, right? And that's equal to the sine of X. And y'all, again, that's just, I'm using this formula right here. The sine of A plus B is equal to this, okay? The sine of A plus B is equal to that, all right? So let's write it down, sine X cosine X plus cosine X sine X. Okay. Now, what is this? What's another way? Something plus something is equal to 2 times the something, right? So what we get here is sine of 2x. Now these, if you look at it, these are just the same 2 terms. You can reverse sine x cosine x, sine x cosine x, right? So this is equal to 2 sine x cosine x. See there, folks? See how these things just keep unfolding, giving you all these miracles? Really? Well, not so much, but you can actually, this stuff comes up again. It really, in calculus, you will see it occasionally. I'm not saying it comes up every day in calculus, But y'all, this is called a double angle identity. Double angle identity. Okay. Now I'm going to give you a homework problem for this one. I'm just going to make this one up. Let's say that you're given, let's say you're given that the sine x is equal to 1/3. Okay. Sine x is equal to 1/3. Okay. Now, instructions here would be to find, I'll just work this one for y'all folks. It's better rather than just expecting you to do it. We're going to find the sine of 2x. Now, folks, some people will leave the parentheses out. I kind of like to put the parentheses in once your argument is something other than just kind of a single letter. Okay. Now, so we're in fairly good shape if you think of it like this. Okay. We already have a big chunk of it given to us. We know from the given information that this would be equal to 2 sine x is 1/3, 2 times 1/3 times cosine x, right? Now, so all we need to do is determine cosine x in order to figure out what the sine of the double angle is. All right. Now, y'all, again, I'm sure a lot of you guys remember that one of the most basic identities is the sine squared plus cosine squared equals 1, Pythagorean identity. Still on the screen. Yeah, there we go. Okay. So you see, we are given that the sine is 1/3. So this would become 1/9. Okay. Plus cosine squared x equals to 1. Okay. This leads to cosine squared x is equal to 8/9. Now, so I think some of you may be anticipating where I'm going with this. If you take the square roots here, you get a plus or minus. So you would, let's write down cosine x is equal to plus or minus. That's you can call it the square root of 8 if you want. It's 2 root 2, but we can just call it √8/3, right? Not really that important to simplify that here. Right? Doesn't really make much difference. This would be the same as 2 root 2, but as far as the problem goes, you don't really need to worry about that. Now, notice here, folks, that so now we know that cosine x, we have something for cosine x, it's bivalued though. So how would we resolve this ambiguity? Okay, well, one way to deal with this is to state what quadrant the angle's in. So what if we said that x was in, and again, I should have probably, but you kind of see why you need these initial conditions. I'm going to go ahead and say that x is in quadrant 2. What does that mean for x to be in quadrant 2? That means that it's between 90 degrees and 180 degrees, right? So in other words, if you want to write this as 90 degrees is less than x is less than 180. And I could have given you the information that way also. I could have just flat out given it to you in either form. I could give it to you as this inequality, where you have the angle trapped between these two quadrantal angles. Or I could just tell you it's in quadrant 2, but these two statements are equivalent, right? And the textbook or the various sources will give it to you like this. Some will give it to you like this. But in any event, what do we know about the cosine in quadrant 2? Well, quadrants 2 and quadrants 3, the cosine of the angle is going to be negative, right? It's going to be negative in quadrants 2 and quadrant 3. So we can reject the plus sign here because of this initial condition. So you see, this really will be stated. I just left it out because actually I forgot. But you see the necessity of having this initial condition specified. Okay, so let's finish this thing off. So this is equal to 2 times 1/3, okay, times the cosine of x, which we found to be minus root 8. Y'all, let me put the minus out here if you allow. A little cleaner, okay. So you got root 8 over 3. Okay, now y'all, we can clean it up just ever so slightly. I'm not too worried about this kind of stuff. But would this be minus 2 over 9 times the square root of 8? Okay. Right, folks, you got the 2 3's down here. 3 times 3 is 9. The minus hangs in. There's your exact answer, ladies and gentlemen. Okay. So there we go on that. Now, so y'all, for your homework problem, I want you to do homework problem number 3. Homework problem number 3. Very same kind of problem, except we're going to be given that I'll give you cosine this time. Cosine of x is equal to 3 over 5. You'll notice I have to pick numbers less than or equal to 1, right? Trap between -1 and 1. If I said 6 over 5, you'd know I was full of it, right? Remember what's the domain of the cosine function? Any number between -1 and 1. So I'm not just arbitrarily picking numbers. I'm picking numbers between -1 and 1. Otherwise, this thing wouldn't fly. Okay. Given this, and also we'll say that x is in, we'll say x resides in quadrant 4, okay, Q4. Of course, you guys remember that's between 270 and 360. Quadrant 4 is any angle between 270 and 360, or 3 pi over 2 and 2 pi. Okay. Find okay. So again, y'all, that's homework problem number 3. I like to do a little bit more, y'all, but I think that probably it's a good move to slow it down and keep the videos less than or equal to 30 minutes. All right. So again, I hope this finds you well. I hope you're staying sane. I know it's tough. Now, y'all, I do want to mention one thing before I sign out of here. You guys, and I may have already said this, and I apologize if I haven't, but this is regarding the way the finals are going to be administered. If you guys have not received, you all should have, the registrar should have sent you the final exam schedule. Now, you all know that what's happened here is they're going to string it out 6 or 7 days. A lot of people aren't particularly happy about that. I know that they have their reasons, but your final will be, let's see, you guys are period 3, right? So your final will be at 9:50. Now, I'll probably just start it at 10. It'll be a Zoom proctored final, and I'll post that in Canvas. There won't be any doubt about it as the date approaches. But it'll be a Zoom proctored 2-hour final, very similar to the quiz you guys took in the Zoom environment. And again, they're doing it like it's basically one final a day. They did it that way. I guess they just thought it would be easier to do things in terms of everybody being organized with their online delivery, and students too. But it is a departure from how the finals have usually been. Finals usually take, what, 3 days? But again, the finals will be stretched out over 6 or 7 days, I think. And you can see your, I'll try to post that for you, but you need to rely on the schedule they sent you. I'll try to post it and confirm it for you guys. But it will happen exactly at our class time. Okay, it'll happen at our class time. I'll start it, I can be there at 9:50 if you want. The way Zoom's set up, you have to start everything on the hour, but I can check in early. But anyway, it will be at our class time, which is 9:50 on whatever that day is in May. Somewhere in early May, I think May, somewhere in there, like 6th, 7th, 8th, 9th, 10th, somewhere in there. But again, just be aware of that as the time approaches. We still got plenty of time, but the final's not too far away, and that's how we're going to handle it. Okay, everybody, y'all take care, and until next time.